Hello, so I'm going to begin lecturing about fluids. I am only going to go one section at a time as to not bombard you with information, but I am going to talk just a little bit about fluids in general to start out. So fluids consist of two different sections, okay? So we're going to talk first about static fluids. And when we do that, we're going to talk about fluids when they're at rest. So we'll talk about, pressure on a cube at the bottom of the sea or on a diver's gauge or head. And we're going to talk about density and some more simple things, but also we'll get more advanced, but just non-moving fluids. Then we'll have a quiz. So you'll have some work, I'll do the lecture, you'll have some work to go with this, and then I'll do the quiz. And that is chapter 11 in OpenStax. Then I will move on to flowing fluids. So flowing, we call that dynamic fluids. Okay, so we'll talk about what happens when a fluid flows and how we can control that, okay? So section 1, and that's all I'm going to do today. Properties of fluids and pressure. Just for the record, I can't, on the place I'm working, I can't have it be a timed slide. So it is normally a timed slide, but it just won't be. So try not to jump ahead in your brain and just stay with me. I am going to try to move that. Okay, so density, you probably know a little bit about density, or at least you've heard about it before, but density has the symbol rho, okay? That looks like one thing, but maybe you'll see it a little more cursive-y, okay? It looks like a little P, but it is a Greek symbol for R, actually, rho. So rho is equal to m over v. Well, m is mass, v is volume, so density is equal to mass divided by volume. Hopefully that is not the first time you've ever heard that density is equal to mass divided by volume, but it is part of my curriculum to teach you that, so I will. SI units for this are kilograms per meter cubed. Now, if you are in chemistry, or have been in chemistry, generally they do grams per centimeter cubed, which are a little bit different. So if you know like the density of water in grams per centimeter cubed, good for you. But what I want you to memorize is that in kilograms per meter cubed, the density of water is 1,000. Now, you do not need to memorize that. I think it is given to you somewhere on your AP exam, or it has to be given to you in the problem, but it is helpful for you to just know this fact throughout the year. So density of water is 1,000 kilograms per meter cubed. So it does say here, memorize. So go ahead and do that. So this is common sense, but I'm going to, again, some of this stuff in the beginning goes a little slower, but it's a good way to start and just see my teaching style and also practice making these videos. If the density of the substance is greater than that of water, the object will sink. If the density of the substance is less than that of water, the object will float. Woohoo! All right. So this thing comes up every once in a while called specific gravity, which sounds a lot scarier than it is. In fact, when I hear the name of it, I feel intimidated. And years ago, if somebody would have thrown at me, what's specific gravity? Even having known a lot of physics, I might be like, oh, what is specific gravity? Because it's just something that's poorly named. All it is a ratio of densities, and what the purpose of it is that it tells us how much of an object will sink below the surface when it does float. So if you put a cork into the water, right? You know it's not going to sink, and it's not going to float all the way on top. Some of it's going to sink and some of it's going to be above the water. So we want to know how much percentage is below, or you might be asked what percentage is above. So that is a purpose of specific gravity, but let's talk about what it is first. It's simply the ratio of the densities of two different things, an object and a liquid. In general, Meaning if you just hear specific gravity, so I know that you're like, in general, that's obvious, but maybe not. Okay, in general, meaning that if somebody just says the specific gravity of something is a number, they are comparing that to water. What would happen to that object in water? They might say a different thing, like, what is the specific gravity of an object in mercury? Well, that's not going to be your regular specific gravity, okay? So specific gravity of water is going to be 1. Oh no, my pencil's gonna die. If specific gravity is greater than 1, the object will sink. If the specific gravity is less than 1, the object will float. So the reason why the specific gravity of water is 1 is because if the substance is water and rho is water, the H2O is water, right? 1,000 divided by 1,000 is going to be 1. Okay, it's because the rho of water is 1,000 and rho of water is 1,000, so that's going to be 1. But if we put something else on this, then we are going to certainly get a different specific gravity. So if when we come up with this, the specific gravity is greater than 1, the object is going to sink. If it is less than 1, the object will then float. All right. So again, I did talk about this a little bit already, but I like to introduce it earlier. So how it's useful is that things do tend to float. They don't tend to sit on top of the water. And I already talked about this, but it does. This is really important to point out. It tells you the percentage of the material below the water. And you know, AP, they almost always will ask you, what is the percentage above the water? So you need to go ahead and make sure that you know whether it's asked below or above, and you need to know that the specific gravity tells us how much is below the water. So let me give you, I think the next thing is an example. Oh, it's not. Oh, well, it just tells you here. Okay, so again, in general, meaning in water, it's going to tell you in water, the specific gravity is the density of a substance over the density of water, but you can do it in any object, any fluid at all. In the denominator, instead of rho H2O, you would go ahead and put rho of that. So maybe you would put the density of mercury instead of the density of H2O. So instead of 1,000 being at the bottom, it would be what the density of mercury is, which I'm a little rusty, so I don't know it off the top of my head, but I will by the end of this section. So you would just change the denominator to the density of the fluid that we're actually talking about. All right, so specific gravity of gasoline is 0.72. So this asks a ton of questions, but I just want to talk to you about just that idea of specific gravity quick. So if it's 0.72, it tells me that 72% is going to fall below the line. Okay, so it's going to fall below that water line. So if you had, and I'm going to try to draw you a little picture on the side here, if this were our fluid, okay, and I'm trying really hard in my head to think of what color I should make gasoline. Gasoline because it's clear, right? So let's see, I'll make it white. How about that? So when we go ahead and put that on top here, well, yeah, it is, you could see it floating because, you know, you've been to a gas station and, well, I'm hoping you've been to a gas station before, and you've seen that if somebody spilled a little gasoline on a puddle, you're going to see that floating on top. But some of it's going to float on the bottom, and actually 72% of it will fall below that water line. So some of it is on top, but there is still a lot into the water. So we're not confident enough to drink out of the bottom of that puddle. All right. Okay. So the whole idea is that 72% of the gasoline that is poured on the water will fall below the line, will be in the water. Bam, got it. Okay. So again, I didn't time these slides because I can't in this program. What is the density of gasoline and does it float? So yes, it floats because the specific gravity is less than 1. So straight up, it floats. We know that. To find out the density, we're going to use our specific gravity equation that I gave you in the previous slide, the rho of the substance over the rho of H2O. We know rho of H2O is 1,000 because we memorized it. So we're just going to rearrange this so it's specific gravity. Oops, I'm just going to change my color so it's not white. Specific gravity multiplied by 1,000. Oops. And we're going to get 720. So you're like, oh my gosh, all I had to do is multiply by 1,000. That is the point of me telling you this. That's all you need to know. If you know the specific gravity of something and you know you're talking about an object in water, you just move the decimal 3 places to the right to get to the density. Okay, so they're going to just trick you by using this fancy word, specific gravity, and it's really just giving you the density divided by 1,000. So just multiply by that by 1,000 and you have the density, and that's all you need to know. And then the other way it's useful is by how much it tells you is percent below. So if it asked us what's a percent above, I'm going to use my calculator because I can't do simple math. I get 28% would be above the water line. So just watch out for those little terrifying little tiny things that they're going to say. All right, moving right along. Example 2. Again, it gives you the answer, so just let's try to pretend that's not there. Can I do this? Oh no, that didn't work. I think I can do this. Not that you can't pause and go back. There we go. And I'll just erase as I go on. All right. So a block of aluminum with a volume of 0.002 meters cubed and a mass of 5.4 kilograms. What is the specific gravity of aluminum? So specific gravity, we know it's the density. Oh, and then obviously, you know, it doesn't have a good symbol. Specific gravity is just one of those things. It's just more annoying, but it can be very helpful. I'll just distract you while I fiddle with this. Okay. Okay, so we have specific gravity, which there we go, FG, is going to be the density of your object over the density of water. Unless it's saying it's not in water, right? So right now we have a block of aluminum. It's not telling us what it's in. We just want to know what the specific gravity is. So our rho, we don't know it. So we're going to have to solve for it. Rho over object, density of the object, is going to be our mass divided by our volume. So the mass is 5.4 kilograms divided by 0.002 meters cubed. And I get 2700 for the density. And I already know the specific gravity then would be 2.7 because I know to divide that by 1,000. But if you want to go ahead and plug it up into the original equation, you can go ahead and do that. 2700 divided by the density of water, which we have memorized to be 1,000, and 2700 divided by 1000 is 2.7. And if I asked you what percentage of this would sink, well, it's 270% of it would sink. So I'm going to go ahead and say the aluminum is going to sink. So obviously you could even use that to see, okay, well, something would sink because 270% of it is going to be below the surface of the water. Okay, example 3. So here is our situation. A piece of ice is sitting in a vat of honey. So now we are into a more difficult thing. And I'm just going to quickly, I know you could always cheat on this, but I'm just going to try to not let us cheat. All right. So a piece of ice is sitting in a vat of honey. Only 35% of that piece remains above the honey. What is the density of honey? So first of all, we're in a situation where we're talking about honey, ice and honey, which is not something we're used to seeing, right? We're used to seeing ice in water, and that would make this really easy. But it does give us the density of the ice, which is awesome of it. So I'm just going to go ahead and make a little bit of a list of information that I do know. I know the density of the object is 920. I already see, hey, this is in sig fig, so I don't have to do any converting. The density of the honey or the liquid, maybe you want to put the liquid, that is, we don't know. That is a question. And it says 35% of the piece of ice remains above the honey. So again, I can't do simple math, but I know that what the specific gravity tells me is a percentage below, which this is giving me above, so I have to do 100 minus 35 to find out that 65% stays below, or the specific gravity is 0.65. That's what the specific gravity is going to be, because that's a percentage below the honey. And we are trying to find the density of the liquid or the honey. So we're going to use specific gravity is equal to the density of the object over the density of the liquid. We are going to rearrange. The density of the liquid is equal to the density of the ice over the specific gravity. 920 over 0.65. And if I do 920 divided by 0.65, I get 1415. And SI units are kilograms per meter cubed. All right, let's see how I did. How come it's not letting me erase? No, it's saying no. I don't know why. Oh, there we go. I don't know what it was doing. Oh, well, there we go. It didn't really, that's the answer. Okay, I had the same work. I don't know why it's not giving me the answer. Okay. That is going to, don't worry about what that says, okay? That is going to be my lecture for this time.